Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 2, A Tour of the Universe. I think that every introductory astronomy class should begin with a general tour of the universe to give you a sense of the sky, the scale, and the size of our universe. By the end of the lecture today, you should have a good idea of where we're located in the universe and how vast the universe is, but also how ancient the universe is. And along the way, you will probably get the feeling that you and I are small and insignificant compared to the size of the universe. So let's talk about something that everyone is familiar with, and that's our planet Earth. So here's a picture of the Earth and the Moon. It's actually one of my favorite pictures of the Earth and the Moon together. It was taken by the Galileo spacecraft as it left the Earth on its way out to Jupiter. They turned the spacecraft around, pointed the camera at the Earth, and they happened to catch this Earth-Moon image. And I like it for a couple of reasons. One reason I really like it is it shows the Earth and the Moon to scale. The Earth on the left-hand side there has a radius of 6,378 kilometers. 12,756 kilometers its diameter, and the Moon has about 1/4 the radius or 1/4 the diameter of the Earth. So this picture shows the Earth and the Moon to scale. It also shows the correct colors of the Earth and the Moon. You'll notice that the Moon is significantly darker than the Earth, something that we will talk about later this semester as to why that is. Now, one of the ways that I think it is convenient to talk about the sizes and scales of things in the universe is to use a scale model. Scale models have the advantage that we can often better picture what's going on when we take the vast distances we're talking about and scale them down to something that we can think about. So if you think about the size of the Earth, for example, you and I probably don't have a really good feeling for how big the Earth is, because compared to just our planet, most of us are fairly small and insignificant. Now, most of us have probably traveled long distances at some point, so we have a good feeling for what it's like to travel from one part of the Earth to the other. Maybe you've been lucky enough to travel halfway around the Earth and you realize how long that took on an airliner flying 600 miles an hour. But we're going to build a scale model, and the basis for my scale model will be a standard classroom globe of the Earth that has a diameter of 12 inches. So all of you have probably taken introductory classes or had a schoolroom at some point that had an Earth globe inside of it. And this standard 12-inch Earth globe is going to be the basis for our scale model. So I'll leave it back here just to remind us of that. If that is the size of the Earth, then the Moon is 1/4 the size of the Earth. That globe is 12 inches in diameter, which means the Moon is represented by a globe that is just 3 inches across. This is a small styrofoam ball, and that is the Earth and the Moon shown to their correct relative sizes. So that is the size of the Earth compared to the size of the Moon. Now, the one thing that isn't correct, both in this photograph and in me holding the Moon up against the Earth there, is the distance from the Earth to the Moon. The photograph that you see here, taken by the Galileo spacecraft, was taken at a special moment in time when the Earth and the Moon lined up together. The Earth and the Moon aren't that close together. So the question is, in our scale model, how close are the Earth and the Moon? So I want you to use Learning Catalytics. So go to Learning Catalytics for this session, and here is our first question of the day. In a scale model of the Earth and the Moon, with a 12-inch globe representing the Earth and a 3-inch globe representing the Moon, what is the proper scale distance from the Earth to the Moon? That is, to get the proper scale distance from the Earth to the Moon, do I need to hold the Moon 6 inches from the Earth? Do I need to hold it 36 inches from the Earth? Do I need to hold it 6 feet from the Earth? Do I need to hold it 30 feet from the Earth or 300 feet from the Earth? So go ahead and use your intuition and answer this question in Learning Catalytics. This is not one of those questions that I expect you to know the answer off the top of your head. The goal here is to get you to start thinking about it and to see what your intuition is like, to see how close you come with your intuition. So take a second. You may pause the video here to go ahead and answer the question in Learning Catalytics. All right, welcome back. Now that you've answered the question inside Learning Catalytics, the right answer to this one is D, 30 feet away. If we were to draw a scale model of the Earth-Moon system, we see that the Earth and the Moon are separated by about 384,000 kilometers. That's about 238,860 miles. Another way to put this is if the Earth is 1 foot across, the Moon is about 30 Earth diameters, or about 30 feet away from the globe. So in fact, for my scale model solar system here, to get a correct distance from the Earth to the Moon, I would need to take this Moon and walk 30 feet away from the Earth just to get the proper scale distance from the Earth to the Moon. As we'll see here in a minute, another way that astronomers measure distances is how long it takes light to cover that distance. And from the Earth to the Moon is 1.28 light seconds. Light travels 300,000 kilometers per second, about 186,000 miles per second, and it takes 1.25 seconds for light to get from the Earth to the Moon or from the Moon to the Earth. Well, now that we've started our scale model with the Earth and the Moon system, let's come a little bit closer to Earth and think about the International Space Station. Right now, orbiting the Earth is the International Space Station. It typically has a crew of 6 astronauts living and working on board. The International Space Station has been continuously occupied for nearly 20 years now. The first astronauts started in late 2000, and the International Space Station has been occupied by astronauts nonstop since late 2000. To put that in perspective, for most undergraduate students today, that means the International Space Station has been occupied their whole lives. And that makes you the very first generation that can say that for your whole life, people have been living and working in space. The question is, where is the International Space Station on our scale model? On our scale model with the globe of the Earth, is the International Space Station very close to the Earth? Is it about halfway to the Moon? Is it very close to the Moon? Or is it about twice as far away as the Moon? So again, you can pause the lecture here, go into Learning Catalytics, answer this question. How close is the International Space Station from the Earth in our scale model? All right, now that you've taken a guess at how far the International Space Station is away, let me show you on the scale model. I mentioned that the Moon is about 30 feet away from the Earth, and so if I walk across the room and put the Moon 30 feet away, that's where the Moon would be. The International Space Station is orbiting about 250 miles above the surface of the Earth. When it comes to our globe right here, 250 miles is about 3/8 of an inch, or about 1 centimeter above the surface of the Earth. So that is where the International Space Station is orbiting. Now, a couple interesting things about space exploration. The last time humans visited the Moon was back in 1972. The most distant that humans have ever been in the universe is to the Moon, and that's 30 feet away on our scale model solar system. But since 1972, humans have gone no further from the Earth than that. That is the distance that humans have gone since 1972. All right, let's continue with some of the other bodies in our solar system out there. So let's start with the sun, of course. Those of us at the University of Virginia are familiar with the rotunda, and the rotunda makes a good scale for, or a good starting point to talk about the size of the sun. The diameter of the rotunda from side to side is about 75 feet. That circle that Jefferson designed the rotunda on has a diameter of about 75 feet. On our scale model, where the Earth is represented by that globe that is 1 foot across, the sun is somewhat bigger than the rotunda. It's got a diameter of about 109 feet across. So if you stand on the lawn looking at the rotunda and can picture how big the rotunda is, now imagine the sun being somewhat larger than that. Again, 109 feet instead of 75 feet across. So it's about 1.5 times bigger than the rotunda. Now the question is, in our scale model, if the sun is represented by a globe that's 109 feet across, how far away would it be? And again, I don't want you to look up or compute the answer to this. I want you to use your gut feeling on this one. So your gut feeling is, if the Earth is that globe about 1 foot across and the sun is a globe about 109 feet across, how far away would it be from the Earth? So again, you can pause the video here, go into Learning Catalytics, take a second to answer the question and then come back to the lecture. Okay, welcome back. If the sun is 109 feet across and the Earth is represented by that globe behind me, the distance from the Earth to the sun is c, about 2.2 miles. That is, if we think of Charlottesville for a second, if we put the sun on the eastern end of the downtown mall, that's where the pavilion is, on the eastern end of the downtown mall, then the Earth is about the right distance when it's on the grounds of the University of Virginia. So that's a good scale model of the Sun-Earth system. The sun being about the size of the pavilion on the east end of the pavilion, on the east end of the downtown mall, with the Earth being 2.2 miles away and being about a foot across. And with the moon, of course, being about 30 feet away from the Earth. So let's talk about the other bodies in our solar system. This is a diagram that shows you the proper scale sizes of the bodies in our solar system. So when you look at the bodies in our solar system, people are often surprised to realize that the Earth is only the 5th largest body in our solar system. Jupiter, Saturn, Uranus, and Neptune are all significantly larger than our planet. And then we have Venus, Mars, Mercury, and then finally Pluto, Eris, and Ceres out there, the dwarf planets in our solar system. We'll talk much later in the semester about all the bodies in the solar system and their sizes. We'll talk about why Pluto was demoted from being a planet. But for now, know that we have 8 planets in the solar system, the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, also called the Jovian planets, and then the 4 terrestrial planets because they're like the Earth, Mercury, Venus, Earth, and Mars. Now this diagram, although it does a good job of showing the correct scale sizes of the planets, it does not show you the correct scale distances to the planets. And so if we wanted to do the scale distances on our scale, where the sun is 109 feet across, the Earth is that globe behind me, we can lay out this model solar system. So to lay out that model solar system, let's think about one of the more distant objects in our solar system, not the most distant object, but a very distant one. And let's talk about Pluto right here. On this scale model, where the Earth is 12 inches across, the moon is 30 feet away from the Earth, the sun is 109 feet across and 2.2 miles from the Earth. The question is, how far is Pluto from the sun? So in Learning Catalytics, answer this question. On a scale with the sun being 109 feet across, the Earth 12 inches across and 2.2 miles from the sun, how far from the sun would Pluto be? So again, pause the lecture, go into Learning Catalytics, and answer this question. All right, now that you've had the chance to answer this question, let's go over what the right answer would be. If the sun's 109 feet across, and the Earth is 2.2 miles from the sun, it turns out that Pluto is D, about 88 miles from the sun. In fact, we can lay out our whole solar system here on our little scale model, with the Earth having a diameter of 12 inches. It is 2.2 miles from the sun. Other planets, you can see that Venus is almost the same size as the Earth, just a little bit smaller. It's about 1.5 miles from the sun. Mercury is a little bit less than 5 inches across. It's a little bit less than a mile from the sun. Mars is 6 inches across, and it's about 3.5 miles from the sun. Jupiter is huge. It's over 11 feet across, and it's also about 11 miles from the sun. Saturn is a little smaller than Jupiter at 21 miles from the sun. Uranus is about 40 miles from the sun. Neptune is about 7 miles from the sun. And there's Pluto out there at 88 miles. And little Pluto is just 2 inches across. And that gives you an idea as to why Pluto was demoted from being a planet, is that Pluto is so much smaller than the other planets in our solar system. Maybe a way to visualize this is to use the state of Virginia. So most of us are familiar with the size of the state of Virginia. Centrally located, we have Charlottesville and Albemarle County right there. And what I have laid out here are the orbits of some of the planets in our solar system. These are the orbits of Jupiter, Saturn, Uranus, Neptune, and Pluto. The orbits of Mercury, Venus, Earth, and Mars are so small that they all fit inside Charlottesville or just outside Charlottesville. And they're so small that I can't show them on this diagram, but I do show you Jupiter, Saturn, Uranus, Neptune, and Pluto. So this is the size of our solar system on a scale model where the Earth is represented by a globe that's 1 foot across. Now, this scale model also points out why astronomers typically don't use miles or kilometers for measuring distances in the solar system. And that's simply because the distances are so large that miles and kilometers no longer work very well. So astronomers have defined a couple different units that we use and will be using throughout this semester for measuring distances to objects both in our solar system and outside our solar system. In our solar system, that is the system of our sun and its planets, we typically use the astronomical unit. The astronomical unit is defined as the average distance from the Earth to the sun. In miles, 1 astronomical unit is equivalent to 93 million miles. It's also equivalent to about 149.6 million kilometers, or in scientific notation, that's 1.496 times 10 to the 11th meters. Now, outside our solar system, even the astronomical unit is too small, and astronomers use light travel time. And the most commonly used distance in light travel time is the light year. It's defined as the distance that light travels in 1 year. Light travels 300,000 kilometers per second, about 186,000 miles per second. So if you take the number of seconds in a minute, the number of minutes in an hour, the number of hours in a day, and days in a year, you can calculate how far light travels in a year, and that turns out to be about 9.461 times 10 to the 15th meters. It's a really long distance, but a light year is simply the distance that light travels in 1 year. It's equivalent to about 6 trillion miles. 1 astronomical unit is about 8.3 light minutes. So one way to think about that is that means the light that we're seeing from the sun takes about 8.3 minutes to get to us. We don't see the sun as it looks right now, but we see the sun as it looked about 8.3 minutes ago, because it took light from the sun 8.3 minutes to get to us. So now let's go back to our solar system for a second. So we've talked about the bodies in our solar system. Let's talk about how far humans have explored. I mentioned that the furthest that a human has ever been from the Earth is to the moon. With the Apollo missions back in the late 1960s and early 1970s, humans visited the moon. And since 1972, we have not been back to the moon. Since 1972, all of our space activities have been confined to low Earth orbit. So when it comes to human exploration, that is actually sending humans into space, the furthest they've ever been on our scale model is about 30 feet away. That is at the distance to the moon. Since 1972, they've only been about a centimeter from the surface of the Earth. But what about robots? How far have robots gotten in exploring the solar system and beyond? So take a moment to answer this question in Learning Catalytics. The most distant spacecraft that we have, if you're curious, we'll see it here in a second. It's called Voyager 1. But the most distant spacecraft that we have is A, much closer to us than Pluto, about the same distance as Pluto, farther than Pluto, but not nearly as far as the nearest stars, about the same distance as the nearest stars, or much farther than the nearest stars. So again, go into Learning Catalytics, pause the video here, take a moment, answer this question. Don't worry about whether you get it right or wrong. For this one, I just want your gut feeling as to what you think is the correct distance from the sun to the most distant robot that we've ever launched. Okay, now that you've had a moment to answer that question, let's talk about that most distant spacecraft. The most distant spacecraft we have is Voyager 1. It was launched back on September 5th, 1977. And as of June 12th, 2020, it is about 149.52 astronomical units from the sun. That means it's about 149.5 times further from the sun than the Earth is. In terms of kilometers, that's 22,368,000,000 kilometers. Or in terms of miles, that's 13,899,000,000 miles. I think a much more impressive number is the light travel time out to Voyager 1. Right now, the light travel time is 20 hours, 37 minutes. Now remember, light travels 300,000 kilometers, which is 186,000 miles per second. And the length of time it takes you to say 1,000, light travels 186,000 miles. Yet the time it takes light traveling that fast to get from Earth out to Voyager 1 is 20 hours, 37 minutes. If I were to broadcast a signal to Voyager 1 right now, it would take 20 hours and 37 minutes for that signal to get out to Voyager 1. The Voyager 1 spacecraft would receive that signal, and it would respond almost right away that it heard me, and it will take its response 20 hours and 37 minutes to come back. The round-trip time from when I send the signal for it to get out to Voyager 1 and for Voyager 1's response to come back is over 41 hours. If I send this signal to Voyager 1 right now, I won't hear back from it for over 41 hours. That's how far away the Voyager 1 spacecraft is. Voyager 1 right now is leaving our solar system. It's traveling about 17,000 kilometers per second. That's about 38,000 miles per hour. It is also the fastest spacecraft we have right now that is leaving the solar system. And the fastest spacecraft we have right now that's leaving the solar system is traveling at 0.0057% the speed of light. That is 0.000057 times c, or the speed of light. On our little scale model of the solar system, where the Earth is a foot across, the moon is 30 feet away, Pluto is 88 miles from the sun out there up in northern Virginia. Question is, how far is Voyager 1? Well, on our scale model of the solar system, Voyager 1 is in New York City. So it's just entering New York City. That's where Voyager 1 is on our scale model. And of course, Voyager 1, the spacecraft itself, is only 10 feet across. So it's a tiny little dot on our scale model. But it is out there at the distance to New York. So this is our scale model of the solar system, showing you all the bodies in the solar system and all their distances from the sun. Now, I mentioned briefly the relative sizes of things. I do want to go back and talk about the sun for a second as the largest body in our solar system. So the sun is the largest body by far in our solar system. It's 109 times the diameter of the Earth. The sun is made completely of hydrogen and helium gas. It's about 74% hydrogen, about 25% helium, and about 1% everything else. So oxygen, iron, carbon, nitrogen, phosphorus, all those things make up about 1% of the sun. It's 24% hydrogen, 74% hydrogen, 25% helium, and that 1% everything else. If you've been looking carefully at this diagram, you might have noticed over there on the right-hand side, right next to the sun, a little tiny blue dot. That little tiny blue dot is the Earth. Now, of course, it's not at the right distance from the sun, but it does show you the proper size of the Earth compared to the sun. That little blue dot is the Earth, 109 times smaller than our sun. And to put that little blue dot in perspective, Carl Sagan has a beautiful poem called The Pale Blue Dot. And in there he points out that that little blue dot, that's you, your family, your friends, everyone you've ever known, everyone who's ever lived has lived on that little tiny blue dot next to the sun. Now, if we put the other planets in our solar system to scale, there they are to scale with the sun. So we can see that even giant Jupiter, which is 11 times the diameter of the Earth, Jupiter is over 300 times the mass of our Earth. Even Jupiter is dwarfed in comparison to the sun. And I want you to keep this picture in mind because this picture does a great job of showing you the difference between planets and stars. For the most part, stars are huge. They're very much larger and very much more massive than planets. For the most part, planets are small and stars are large. So keep that in mind as we go through the rest of the semester and we talk about the stars out there. Our sun is a fairly typical star. There are stars that are larger than our sun, stars that are smaller than our sun, but our sun is a I would say it's a medium-sized star. It's actually larger than your average star, but it's a medium-sized star. When you look up there in the night sky and you see the stars up there in the night sky, it's important to remember that most of the stars that you can see with your naked eye without a telescope are actually much bigger than our sun, much more massive than our sun, and much more luminous than our sun. But in any case, our sun is a medium-sized star. Later in the semester, we'll talk about the fact that the bodies in our solar system fall into three types. There are the hard, rocky terrestrial planets, the gas giant planets, Jupiter, Saturn, Uranus, and Neptune, and then the cold, icy bodies out there at the edge of the solar system, things made primarily of water ice like Pluto and Eris. But we'll leave that for later in the semester. To talk about the different types of bodies. I'm also not a big stickler on the number of planets. I know that there are people who still believe that Pluto should be a planet. There are people who believe that not only Pluto, but that Eris should be a planet. There are those that believe that even the large asteroid Ceres should be a planet. So I'm not a stickler on knowing the number of planets, but later in the semester we will see that I think it is important to know that there are three types of bodies in our solar system. The hard, rocky ones, the gas giants, and then the cold, icy bodies. Well, let's continue our scale model solar system here for a second. Now that we've covered the solar system, let's talk about some of the bodies outside our solar system. And that would the next body outside our solar system that we want to talk about is the next closest star, and that is Alpha Centauri. So this is a picture of the southern sky, and this is the beautiful constellation of the Southern Cross. Three bright stars and one moderately bright star make up a beautiful cross in the sky. It's not visible here in the continental United States. We are too far north. The Southern Cross is too far south for us to be able to see. But it is a beautiful constellation because of the three bright stars and that moderately bright one. If you get out under dark country skies, you can see the beautiful Milky Way arcing behind the Southern Cross and a very dark nebula next to it called the coal sack. This is actually a giant cloud of gas and dust that is between us and the distant stars of the Milky Way that is blocking the light from some of the stars in the Milky Way. Next to the Southern Cross in the sky, we have the constellation of Centaur. And in Centaur, the two brightest stars are Alpha and Beta Centauri. And Alpha Centauri is the star that is closest to our solar system, it's the closest star to us other than our sun. So our sun is obviously the closest star, but Alpha Centauri is the closest star system other than our sun. Now, Alpha Centauri is a multiple star system. It's a binary star, two stars going around one another with a third star that's far away that's orbiting the two of those. And that third star happens to actually be closer than the Alpha Centauri pair. Its name is Proxima Centauri, but it's not visible with the naked eye. So for now, and it's part of the Alpha Centauri system. So I think just to simplify things, we will say that the Alpha Centauri star system is the closest star system to us. And Alpha Centauri is 4.4 light years away. That is, when you look at Alpha Centauri, you are seeing light that left 4.4 years ago because it's 4.4 light years away from us. It has taken light 4.4 years to get to us from Alpha Centauri. Now, 4.4 years is a long time to a human being. To a star, of course, 4.4 years is a blink of an eye. But on our scale model, what's the distance to Alpha Centauri? In our scale model where the Earth is that globe back there, how far is Alpha Centauri? Well, on our scale model, where the Earth is 2.2 miles from the sun, Pluto is 88 miles from the sun, the most distant spacecraft that we've launched is 332 miles from our scale model sun. Alpha Centauri is a little bit bigger than our sun. It's about 138 feet across, and it is 600,000 miles from our sun on our scale model. That's not its real distance. That's its distance in our scale model, where the sun is only 109 feet across and 2.2 miles from the Earth. To put that in perspective, Alpha Centauri is 2.5 times the distance to our moon. We would have to build a ball that's 138 feet across and transport it 2.5 times further than the moon. What this shows us is that the vast distances between the stars, the distances between the stars are vast and empty. Once we get out to Pluto, for the most part, we've reached the edge of our solar system. There are many cold, icy bodies out there beyond Pluto. They may extend out to a light year or two from the sun, even in a giant cloud of comets called the Oort cloud. But the vast majority of the material in our solar system is located here in the inner solar system. And that inner solar system ends roughly 88 miles from the sun. And for the most part, between that and the nearest star at 600,000 miles on our scale model, there's almost nothing. Like I said, they're cold, icy bodies. There are probably trillions of comets out there, but they're all very small, and the distances between them very, very large. So, problem with this is if we try and do anything else in the universe, these distances are so large that you and I have no idea what 600,000 miles looks like, right? I don't have a good intuition for what 600,000 miles look like. So we're going to do something different. We're going to have to shrink our scale model down. And we're going to have to shrink our scale model down so that the distance from the sun to Pluto is 1 centimeter. So let's shrink our solar system so that our solar system, our whole solar system, has a radius of 1 centimeter. To put in perspective what that looks like, I've printed out this little plot right here that shows you the sun at the center, and there's Pluto 1 centimeter away from the sun. Okay, so imagine that this is the size of our whole solar system. Of course, the sun should be a tiny little dot down at the center of the page. I didn't even draw the other planets on there because they're all so close to the sun that it would all just bleed together. But imagine that this is the size of our solar system. How far away are things then? Well, in that case, Voyager 1 is about 3.8 centimeters from the sun. So if we've got the sun right here and Pluto right there, Voyager 1 is about 3.8 centimeters away. So it's a couple inches away from the sun on this piece of paper. By comparison, the nearest star, Alpha Centauri, at 4.4 light years away, is about 233 feet, about 71 meters away from us. So it's outside and across the street from where I am right now. The brightest star in our night sky, Sirius. Sirius is bright both because it is an intrinsically luminous star. It's giving off lots of light every second, but it's also bright because it's one of the closer stars to us. It's 8.6 light years away from us. And 8.6 light years away on our little scale model of the solar system, it would be 138 meters away from us. So about 400 feet away or so. By the way, the Voyager 1 spacecraft traveling at the speed that it's traveling right now, if Voyager 1 is not headed towards Alpha Centauri, but at the speed that Voyager 1 is traveling right now, it will take Voyager 1 about 70,000 years to reach the distance of Alpha Centauri. So Voyager 1, it would take 70,000 years to get there. All right, so let's talk about some of the other stars in the night sky. So this time of the year, the Big Dipper is very prominent high overhead. So 4 stars form the bowl of the Big Dipper. 3 stars form the handle of the Big Dipper. Of course, the Big Dipper is an asterism. The constellation is actually Ursa Major, the big bear, with the nose of the bear and the neck of the bear and the body of the bear. A front leg coming down to 2 toes on the front paw. A back leg coming down to 2 toes on the back paw. Another back leg and the big long tail right there. So I pick Ursa Major for talking about the distances to the stars because it's an easy constellation to find. And it also points out very nicely that not all the stars in a constellation have the same distance from us. In fact, in Ursa Major, or in the Big Dipper, these 5 stars all do have about the same distance. They are all about 80 light years away from us. And that's because these 5 stars were born together. They're actually moving through space together. So those 5 stars are related to one another. But this star in the handle and this star in the bowl are not related to the other 5. This one's about 20% further away at 101 light years away. And this one's another 24 light years beyond that at 124 light years away. So those are the stars of the Big Dipper. Other interesting objects in our night sky are the Pleiades, the 7 sisters, a beautiful little cluster of stars that is visible in the winter sky, and its distance is 444 light years away. The Pleiades are 444 light years away. On our little scale model, where the distance from the sun to Pluto is just 1 centimeter, the Pleiades are about 4.3 miles, or about 7 kilometers away. And the Pleiades, in terms of our whole Milky Way galaxy, are our next door neighbor. Now, we live in the Milky Way galaxy. This is our Milky Way galaxy. This is what the galaxy looks like to us living inside the Milky Way. This is a photograph taken from Mount Graham in eastern Arizona. The University of Virginia is a partner with a number of universities. And we operate the Large Binocular Telescope out on Mount Graham. It's the largest telescope in the continental United States right now. And in this diagram, we see a couple things there. So there's a shadow of a tree over here, some other shadows of things, some shadows of some masts right there. We see these two ugly yellow glows right there on the horizon. And those ugly yellow glows, those are the city lights from Tucson, Arizona, and the city lights from Phoenix, Arizona. And then cutting across the middle right here, we see our beautiful Milky Way galaxy. And that's the galaxy that we live in. We'll talk more about our Milky Way here in a second. We'll talk about why it looks like this in the sky. But just know right now that that milky band of light is our Milky Way. Everything that you can see in the night sky, with one exception, is a part of our Milky Way galaxy. All these stars are part of our Milky Way. All these stars are part of our Milky Way. This bright one right here, that's the planet Jupiter. Jupiter is part, of course, of our solar system, which is part of the Milky Way galaxy. Everything you see in this diagram is a part of our Milky Way diagram, with one exception that I'll mention here in a second. If we could get outside the galaxy, this is what our Milky Way galaxy would look like. This is another spiral galaxy. It's got a catalog number, NGC 4414. And if we could get outside the Milky Way, this is what our Milky Way would look like. Our Milky Way galaxy is about 100,000 light years from side to side. That is, it takes light traveling at 300,000 kilometers per second, about 100,000 years to go from one side of the galaxy to the other side of the galaxy. And we don't live out at the edge of the galaxy. We don't live in the center of the galaxy. We live about halfway out in the Milky Way. Our solar system is about 26,000 light years from the center of the Milky Way galaxy. So that's where we're located. Now, you might wonder, if that's what the Milky Way looks like, why does it look like this in the sky? Well, the answer to that has to do with the shape of our galaxy. Our galaxy consists of a giant ball of stars that is surrounded by a rotating disk of stars and giant clouds of gas and dust. And if we imagine what it's like to live inside the galaxy, let's build a model of the galaxy. My favorite model of the galaxy is to think of the galaxy like a pizza. This swirling disk of stars and gas and dust is very, very thin, but it's round and very large. And so the disk of our galaxy is like a pizza. And the center of our galaxy down here is like a giant watermelon at the center of the pizza. It's like a big ball of stars, a big watermelon down at the center of the pizza. So now let's imagine what it's like to live in the Milky Way galaxy, to live in the pizza, and see if we can understand why our Milky Way looks like this. Imagine that you live in a little thin pizza. Inside the pizza, there's not much pizza above you. There's not much pizza below you. But when you look around you, there is lots and lots of pizza around you. So again, imagine living in a pizza, not in the center of the pizza, not out at the edge, but halfway out and halfway between the top and the bottom of the pizza. And again, there's a little bit of pizza above you, a little bit of pizza below you, and lots of pizza around you. In the Milky Way galaxy, because we live in the pizza, there are some stars above us, there are some stars below us, but there are lots and lots of stars around us. And this band of light, this Milky Way, is that band of galaxies surrounding us, that pizza, if you think of it that way, surrounding us. And down at the center of the galaxy, there's the watermelon. There is that big ball of stars down at the center of our Milky Way galaxy. And cutting down the middle of the galaxy right here, this looping dark area, that's not a place where stars are missing. Those are actually giant clouds of gas and dust in the next spiral arm in from us in the Milky Way galaxy that's blocking our view of the distant stars. And you can actually see those giant clouds of gas and dust with the naked eye. If you go out under very dark skies and you see the Milky Way galaxy, you can see that it clearly, distinctly breaks into a brighter part and another bright part right there with a dark lane cutting down the middle. And that dark lane are these giant clouds of gas and dust. So that is our Milky Way galaxy that we live in. So how big is the Milky Way galaxy? On our scale model, where our whole solar system has a radius of 1 centimeter, where the distance from the sun to Pluto is 1 centimeter across. On that scale model, our Milky Way galaxy is about 1,000 miles across, and we live about 260 miles from the center of the galaxy. To put that in perspective, this is what it looks like compared to the continental United States. There's our Milky Way galaxy. and remember, this is the scale model where this is the size of our solar system. So on this scale model of the galaxy, where our galaxy is about 1,000 miles across, this is the size of our solar system, and we're located about 260 miles, about 418 kilometers from the center of the galaxy. So that is our Milky Way. As I mentioned, this is what the galaxy looks like, a thin disk of stars, that pizza of stars with that big ball down at the center. Now, I hinted a few minutes ago that when you look up in the night sky and you see the Milky Way up there, that there's something up there that is not a part of our Milky Way galaxy. And in the fall, if you look in the constellation of Andromeda, you will see a little fuzzy object up there in the sky. It's this thing right here in this diagram. And that thing is the nearest galaxy to us, called the Andromeda Galaxy. And the Andromeda Galaxy is a galaxy just like our Milky Way, and is located about 2.5 million light years away from us, 2.4 million light years away. It's about the same size as our Milky Way galaxy. Actually, it's a little bit bigger than our Milky Way galaxy. But it's a spiral galaxy like our Milky Way galaxy, 2.5 million light years away. And on our little scale model of the solar system, where our galaxy is 1,000 miles across, the distance to the Andromeda Galaxy is about 25,000 miles away. So it too is about 1,000 miles across, and it's 25,000 miles away from us. Now, finally, let's talk about the most distant objects out there in the universe. And the most distant objects out there in the universe are best pictured by looking at this amazing photograph taken by the Hubble Space Telescope. This is the deepest image of the universe that humans have ever taken. It's called the Hubble Extreme Deep Field, or the HXDF. The Hubble Extreme Deep Field is a relatively nondescript part of the sky where the Hubble Space Telescope sat there for millions of seconds just photographing this one part of the sky so that we could take the deepest image that humans have ever taken of the universe. And this is that image. It is, to me, actually remarkably one of the most beautiful and one of the most interesting pictures that Hubble has ever taken. By the way, the patch of the universe that you're looking at right here is much, much smaller than the full moon in the sky. So when you look up and you see the full moon up there in the sky, keep in mind that the Hubble Extreme Deep Field is much, much smaller than the full moon. It's a little tiny patch of the sky that Hubble spent many, many millions of seconds studying so that we could get this image. Now, some of the objects in this, well, in fact, what's interesting about the Hubble Extreme Deep Field is that the vast majority of these objects are galaxies like our Milky Way. Only a couple of the things in this photograph are stars in our Milky Way galaxy. So this is a star in our Milky Way galaxy. That's a star in our Milky Way galaxy. That's a star in our Milky Way galaxy. We can probably find one or two more on here if we look really hard. But those are stars in the Milky Way. Now, because, again, the distances between stars are vast and stars themselves are very small, we can see right through the stars out into deep space. And then we see all these other thousands upon thousands of galaxies out there. And all of these galaxies are like our Milky Way. This is a spiral galaxy like our Milky Way. Seen so far away, it looks like a little fuzzy blob of light. This is a galaxy like the Milky Way. That's a galaxy like the Milky Way. But what's most amazing about the Hubble Extreme Deep Field is even the smallest little dot on here, the tiniest little dot, is a galaxy like our Milky Way galaxy, seen so far away that it looks like a small, tiny little dot. The most distant object in the Hubble Extreme Deep Field is about 13.2 billion light years away from us. That is, it has taken light from that distant object about 13.2 billion years to get here. So on our scale model, where the sun and the moon, and so where Pluto is about 1 centimeter from the sun, the nearest star is over 100 meters away across the street. Our Milky Way galaxy is about 1,000 miles across, with the nearest galaxy also about 1,000 miles across, located 25,000 miles away from us. How far is it out to the most distant object in the universe? Well, the distance to the most distant object in the Hubble Extreme Deep Field is, on our scale model, about 1.5 times further from the sun. That's how vast the universe is. So I hope in this little tour of the universe, I've given you a feeling for how vast the universe is. before we move on to the next topic, which is the age of the universe, I want you to take a moment inside learning catalytics, and I want you to take a moment just to sort these things in their proper order. I haven't sorted everything we've talked about here. I just want you to sort these four because they are the ones that will be often coming up this semester. Take a moment, go to Learning Catalytics and sort these. The way that you're going to do it is in order from closest to most distant. So you will pick the object and then you will use the less than sign, and then you'll pick the next object and then the less than and the next, and do that all the way out to the most distant object. So go ahead and pause the video right here. Take a moment and go ahead and answer this question in Learning Catalytics. All right, now that you've answered that question, I want you to not only feel very small compared to the size of the universe, but I also want you to understand how incredibly ancient the universe is. And to do that, we're going to study something called the universal year. Carl Sagan had this problem when he had his television series Cosmos. He was trying to find a way to explain the history of the universe to people in numbers that were explainable. Because the problem is our universe is 13.8 billion years old. 13.8 billion years is such a long time that you and I have no good feeling for how long that is. But what Carl Sagan realized is that most of us have a very good idea of how long a single year is. And so he said, what if we take the 13.8 billion year history of the universe and cram it into one Earth calendar year? That is, the Big Bang happens on January 1st at midnight, and December 31st at midnight is right now. So let's look at the history of the universe and some of the important events in the universe that have happened in this calendar year. If you're curious, here's how it breaks down. 1 month on this cosmic calendar translates into about 1.1 billion years. A day is about 38 million years. An hour is about 1.6 million years. A minute is 26,000 years. A second is about 430 years. And 0.1 seconds is 43 years. So let's take a look at this. So here is our cosmic calendar. The astronomer Neil deGrasse Tyson has remade the Cosmos series that Carl Sagan originally did many decades ago. And he did that in 2014. And as part of that, he redid the cosmic calendar. So that's why this is a 2014 calendar. I took it from Neil deGrasse Tyson's Cosmos series. So the Big Bang happens on January the 1st at midnight, so that's when the Big Bang occurs. We get our first stars in the universe. So the Big Bang, the universe consisted of lots of gas, hydrogen and helium gas, almost nothing else, but mostly just hydrogen and helium, expanding very, very rapidly. Gravity started clumping that gas together to form the first stars. And so in this cosmic calendar, we get our first stars on about January 13th. That's a few 100 million years after the Big Bang. Galaxies are bigger and harder to assemble. We get our first galaxies by January 16th, but really big galaxies like our Milky Way take a long time to assemble. And our own Milky Way galaxy didn't form until middle of March. About March 15th is when our Milky Way galaxy formed. Our Milky Way built up by cannibalizing many smaller galaxies. Gravity started pulling things together. They made the first stars. Those stars get gathered into the first galaxies, and many of those first galaxies combine together to make our Milky Way galaxy. So our Milky Way galaxy forms about 3 months into the year. Now, an important thing to realize is that our sun was not created in the Big Bang. The Big Bang is the origin of our universe. It is not the origin of our sun and planets. Our sun and planets were born much later. Now, on this diagram, a typical star can live for many, many months, or even on this cosmic calendar, a year or so. So when the galaxy was born on March 15th, there were generations of stars being born, living out their lives and dying. Stars being born, living out their lives and dying. Stars being born, living out their lives and dying. Stars being born, living out their lives and dying. And then 4 generations or so after the first stars in the Milky Way galaxy, our sun forms. Our sun formed on the cosmic calendar around September 1st. That's about 4.5 billion years ago. About 9 billion years into the history of our universe is when our sun forms. Now, not long after our sun forms, and by the way, the planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all the planets, all the icy bodies in the solar system, they all formed at the same time that our sun did on September 1st. Not long after the Earth forms with the sun on September 1st, life appears on Earth. The first hint that we have of life, or I should say the first hints that we have of life, would be on the cosmic calendar in late September. Now, this first life was very, very primitive. It was chemosynthetic. That is, it used chemicals in the ocean. It got its energy from volcanic vents down at the bottom of the ocean. Some of the first complex life that we start seeing, the first photosynthetic life, comes about on October 2nd. So as life starts getting more complex, it starts using more complex chemistry, it starts taking advantage of the light from the sun, and life develops photosynthesis by October the 2nd. This life is taking carbon dioxide from the Earth's atmosphere and converting it to oxygen. So by October 26th, we finally have significant oxygen in our atmosphere. Before the end of October on this cosmic calendar, there was no oxygen in our atmosphere. And the life forms on Earth did not use oxygen. But this appearance of oxygen means that other life forms can take advantage of that oxygen, and they can have even more complex chemistry and use even more energy than the simple life forms we have so far. But so far, keep in mind that all the life has been single-celled life. Well, on November 9th, we get our first eukaryotic life. So up until this point, all the life on Earth have been prokaryotes. Prokaryotes are the simplest form of life. Their cells do not have an individual nucleus. They do not have organelles inside of them. Eukaryotes, and you and I, our cells are eukaryotic. That means they have a cell nucleus. That means they have organelles inside the cells. So on November 9th, they're still single-celled organisms, but we get the first complex cells on Earth on November 9th. On November 29th, we get sexual reproduction for the first time. And this is important because up until this point, when an organism lives out its life, it copies itself for the next generation, and it makes copies and copies. And every now and then, when you make a copy of something, an error will happen in the copying. Now, most of the time, that error results in the offspring dying because it doesn't make them better adapted to their environment. But every now and then, an error in that copying will make the organism better able to survive in its environment, and those organisms will come to dominate. But on November 29th, we develop sexual reproduction. Life on Earth develops sexual reproduction. And now you have two different organisms combining their genes to make a new one. And now evolution can go much faster because now you're taking two gene pools and combining them. You have the opportunity for many more changes to occur. And so what we will see is with the advent of sexual reproduction at the end of November, that evolution travels much faster. But keep this in mind, from the first life on Earth all the way through October and November and into early December, life consisted of single-celled organisms. The first multicellular life occurs on December the 5th on our cosmic calendar. That is the first time we see multicellular life. The first animals, and first complex animals, I should say, appear on Earth on December 17th in an amazing event called the Cambrian Explosion. If you're interested, you should look up the Cambrian Explosion. It's an amazing event on the history of the Earth. Up until this point, life was not very complex, and then there is an explosion in diversity and an explosion in complexity of life on Earth. And interestingly, all the phyla that we have on Earth today were created in the Cambrian Explosion. It has nothing at all to do with a meteorite hitting the Earth. It's called an explosion because it was an explosion in diversity. The phylum that you and I belong to, Chordata, because we have a spinal cord, we see the very first chordate in the Cambrian Explosion, a little tiny animal that clearly had a spinal column, a spinal cord running down its back. There were many other phyla that were created in the Cambrian Explosion that have since gone extinct. But since the Cambrian Explosion, life on Earth has not created any new phyla. All the phyla that we have today are seen in the Cambrian Explosion. And that was December 17th. The dinosaurs come about on December 25th. We get our first dinosaurs on Christmas Day. And the dinosaurs do great because they last on the cosmic calendar 5 whole days. So the dinosaurs come around on December 25th and they go extinct on December 30th. is when the dinosaurs went extinct. Now, this is quite remarkable. The dinosaurs going extinct is something that you and I think of as happening long ago. But on the cosmic calendar, where the Big Bang was on January 1st and today is on January 31st, the dinosaurs went extinct yesterday. On the cosmic calendar, the extinction of the dinosaurs was literally yesterday. If we want to talk about human history, we not only have to look at December 31st, but we have to look at the final few minutes and seconds of December 31st. On the last day of the year, December 31st, early hominids evolve around 9 p.m. Modern humans finally show up on the scene about 2 minutes before midnight. Humans develop agriculture about 25 seconds before midnight. About 11 seconds before midnight, the pyramids are built. About 400 years ago, Kepler and Galileo show that the Earth is orbiting the sun and not the other way around, and that is 1 second before midnight. And today, now, is midnight on December 31st. Everything that we think of as recorded history, all of recorded history, has happened in the last few seconds on the cosmic calendar, where we have the history going from the Big Bang on January 1st, all the way down to the end of the year. All of recorded human history has been in the last few seconds. So our universe is both vast and ancient. And I hope in this lecture I've given you a feeling for how vast it is and that you feel very small and insignificant, but also how ancient it is and that you realize that the course of a human lifetime on the cosmic calendar typically spans 0.2 of a second. That is in the length of time it takes me to say 1/1000. We could have 5 human lifetimes or about 10 human generations in that 1/1000. So thank you very much. In Lecture 3, we will take a look at the night sky and we will study how the night sky looks to us. So thank you for joining me. I will see you in Lecture 3.